This slideshow is on population growth. We'll start with the definitions. So this is a fairly straightforward unit. There are some definitions you need to know and also some calculations. You need to recognize that capital N represents the population size, in other words, the total number of individuals. And if there is a subscript such as O, or that means initial, and if you have T, that's at some future point in time. You also need to know how to calculate population density, population distribution, how this describes the clumping or even distribution of individuals within a population. And you've got sex ratios, which really mean gender ratios, males to females. And finally, an age structure, which determines how many individuals are in a particular age category, such as a cohort. Here are your goals. Let's start with the idea of population models. These are models that use mathematical equations to enable us to evaluate a population, predict the size at any moment in time, and discuss various parameters. So the first thing you can calculate is a growth rate. This is going to give you an idea of what kind of offspring you can include at any particular time, along with the deaths and even the possibly individuals that immigrate in or out. There is such a thing as an intrinsic growth rate. This is the maximum potential with unlimited resources. And as you know, the exponential growth model, which has a very complicated looking formula, but it actually can be broken down pretty easily. So let's look at that. This is the exponential growth model. Here we have a J-shaped curve where the population is growing at a constant rate. The number of individuals increases each time because the size itself is getting bigger. Now this one is pretty much theoretical, or if you would imagine, idealized, because most populations do not have unlimited resources. The second one is going to be the logistic growth model. In this one, it's a little bit more realistic because it does incorporate the environmental limits. So make sure you understand what a limiting resource is, what carrying capacity is, and please notice that it's a K, and that this is going to result in an S-shaped curve. This is a logistic growth model. Notice the characteristics. Initially, very rapid early growth, it's exponential. We have a midpoint where growth begins to slow after that point. And finally, as it approaches carrying capacity, the environmental growth slows and stops. Please note that at the midpoint right here would be the fastest growth rate. And often when managers are trying to manage a population in the wild, they want to keep any kind of culling due to hunting or whatever, to keep that population at kind of its midpoint between the carrying capacity and very low growth to maximize the recovery. So the question comes up, does the logistic model account for both density dependent and density independent factors? Think about that for a moment. Actually, it doesn't. It only deals with the density dependent. The density independent factors, those are pretty unpredictable, and so they're not included in the model. This is a figure from your textbook that looks at a case study of a population of reindeer that were introduced onto St. Paul Island in Alaska in 1910. It's a very small population. The orange dotted line is going to represent what exponential growth would look like. So you can see that this population initially demonstrated exponential growth. And suddenly, then it went through a major crash. So what do you think happened? More than likely, the reindeer grew at such a fast rate that they out-consumed their resources. Think about how you could manage this population to be sustainable on the island. More than likely, you'd need to do some type of culling or some type of migration with the reindeer so that you can prevent the consumption of all of the food resources. This is another graph that's shown in your textbook, and this one points out that often organisms will overshoot their carrying capacity. If you notice the part about the fact that when an organism gets pregnant, it may be several months before the offspring is born, and during that time the resources may change in the availability, and we'll have this growth, rapid growth, where the more organisms are born than the situation can carry. And as a result, then we have little die-offs. And so it will oscillate often around that carrying capacity. Not neatly as this picture, of course. This is a picture, also from your textbook, slightly different version, of the wolves and the moose on Isle Royale. And if you notice, it's a long-term study. It's 50 years. Be familiar with this and be able to identify the events that would be both density independent and those that would be considered density dependent. Kind of discuss examples of top-down control and examples of bottom-up control. So that concludes your population ecology introduction.